Let's try to implicitly differentiate one more time. For specifically x squared plus y squared is equal to 25. That is a circle, right? Definitely not a function. It's actually two different functions. You got your top half of your circle, you got your bottom half of your circle, right? It would look something like this. Maybe I choose two different colors. We've got this positive semicircle, and then we have this, say, this negative semicircle here, right? So now you don't always have to do it both explicitly and implicitly, but we are going to build that kind of relationship between it to show you that they are exactly the same. They're going to get the same exact answer. And it's just that, you know, sometimes this explicit one is either too tough or impossible to do. This one, it's not. We can actually get y by itself pretty easily. But the implicit differentiation, we want to be able to establish that it does give you the same answer that you would get if you did it explicitly. And kind of to reinforce that idea of that chain rule component to it, which is the using that dy dx or that y prime at the end of it. All right, so let's first do this explicitly. That's what that word says. I know it doesn't look like it. Let me fix it. So to do it explicitly, I need to first solve this thing for y. And I think I can do this in one step. I can subtract over the x squared, and then I'll have to take the square root. And in the process of taking the square root, I should get two of them, positive and a negative. So y is equal to plus or minus square root of 25 minus x squared, right? Plus or minus because you got this positive semicircle, minus because you got this bottom one. Who knows what happened right down there? An asteroid? Anyway, and so now we're ready to explicitly take its derivative. Well, almost. I think I'm going to convert it to a rational exponent, thusly, to the 1/2 power. Now notice something, would you? This is a composite function because we have we have 25 minus x squared inside of the square root function, which means when we take the derivative of this, we will have to use the chain rule. Don't forget. Okay, let's write it. dy dx is equal to, leapfrog that power down, plus or minus 1/2 25 minus x squared to the negative 1/2 power. And we're not done yet because we need to now take the derivative of the interior. So taking the derivative of the inside of that, the 25 will go to 0, and then I leapfrog this power down, it would be negative 2x. So times a negative 2x. And you know, let's go ahead and clean this up a little bit. Like one of the things that conveniently happens is this 1/2 and the 2, they cancel each other out. But what about this negative sign that's right here? Notice I already have a plus and the minus out here. What happens when you multiply a negative times a positive and a negative? Well, the positive becomes negative and the negative becomes positive. So really, this becomes minus plus. Yep. Okay. And then let's keep going with it. Let's see. Anything else happen? Well, yeah, I'm going to keep the x up top, and then I will take that square root and cram it down to the bottom. 25 minus x squared. And, I mean, I'm kind of being silly about this minus plus, but really it's important because the top half of this used to be the positive semicircle, right? But whenever I take its derivative, that positive gets multiplied times this negative that I just deleted, this negative, which makes it negative. So the negative of this function is actually the derivative of the top half, and then the positive one is the derivative of the bottom half, okay? All right, so it was actually vital. Now then, let's do all of this implicitly, and you'll see how much more satisfying it is, I think. All right, implicitly. So we're going to take the derivative with respect to x on both sides of this. I had x squared plus y squared. And then do the same thing on the right-hand side where you just have 25. Okay, anything that involves x's, you differentiate normally. Anything involving y, don't forget to apply the chain rule to it. So I'll leapfrog that power down, and we'll have a 2x plus, leapfrog the power down on the y as well, a 2y, but since y is implied to be at least one function of x, we need to multiply it times the chain rule dy dx. Is equal to, what's the derivative of 25? It's just a constant, which means not changing. Its derivative is 0. Our next step is to solve for this dy dx. So I will subtract over the 2y term, 2x term, and then divide by 2y. When I divide by 2y, of course, the 2's are going to cancel, and I'll have dy dx is equal to a negative x over y. Look at this. Compare these two things. Here's the derivative implicitly versus the derivative explicitly. Whoa, I know that it would be much easier to substitute points into this thing than it would be in this one. But is it the same thing? Well, let's see. This says negative x over y, and what was y equal to? Remember, we solved for y right up here. It's equal to plus or minus the square root of 25 minus x squared. So I could rewrite this. Negative x would stay, and then the y would become plus or minus the square root of 25 minus x squared. And then you can see that this negative times this plus or minus would turn it into the old negative plus that was right up there. So it is, in fact, exactly the same. All right, this question's not quite done yet. It did ask us to find the slope of the tangent line to the curve at negative 3, 4. We just plug that number, or that set of coordinates, into the derivative that we just found. And really, we could plug it into either one. I think this one's going to be easier, so that's what I'm going to do. Here's the way that I write that in Leibniz notation. I write dy dx such that, and then an ordered pair, x comma y, is equal to negative 3, 4. So up until this point, whenever we plugged in numbers into our derivative, we only really had to worry about x's because they were functions of x's. But now this is a function of both x and y, so I'm going to need both of these coordinates. It's equal to negative 3, so positive 3, over 4. We've got 3/4 for our slope at that particular point. All right, not too bad, right? Okay, and then, something that I might have to do with it is to write the equation of the tangent line. That should be pretty easy. Y minus 4 is equal to 3/4 times x plus 3. Piece of cake. Okay, let's wrap this up, summarize this just a little bit here. Implicit algorithm, what you're supposed to do whenever you implicitly differentiate. And now the equations that we're going to take the derivative of, they're going to get a little bit more challenging. We've only kind of scratched the surface here, and this is overall what we want to do. Step number 1, you want to differentiate both sides of the equation with respect to x. And that means that anytime that you have x terms, you just differentiate normally. Anytime you have y terms, though, you have to make sure that you multiply it times dy dx using the chain rule. Step 2, you want to move all your dy dx terms to one side of the equation, and then you get everything else on the other side of the equation. So far, we haven't had to worry about that because we've only had one dy dx term, and it's only been on one side of the equation. But we're going to see some more complicated examples where we're going to have dy dx terms on both sides. So we got to gather them up. We got to combine them up on one side of the equation. And then once we've done that, we want to factor out that dy dx term. Because I might have it in multiple terms, we want to factor it out so we can isolate it for step number 4, which is all about solving for that dy dx term. I might have to divide something over. Now, we did have to do that last step on both of the previous examples. Okay, so like I said, when we come back here, hey, where are you going? Where are you going? You're moving around. When we come back to this next video, we're going to look at something maybe a little bit more complicated than just a circle.